Hello friends, in this video I'm going to show Einstein's proof for Pythagoras theorem, and it will be very slow because I'm also explaining the prerequisites that Einstein used to prove Pythagoras theorem. So the great men we are obliged to: Pythagoras, Euclid, and Albert Einstein. This is the picture of Albert Einstein, but Pythagoras and Euclid, we don't know if these are the real pictures, but this is from some artist's imagination. So Einstein set out to prove Pythagoras theorem, which pertains to okay right angle triangles. So this is our triangle ABC. This is the right angle. So Pythagorean theorem is that the hypotenuse, the relationship of hypotenuse with the adjacent perpendicular and base is AC square is equal to AB square plus BC square. So there are many proofs of this. The one that Einstein used to prove does not involve making squares of the sides. So he used principles of relationship among between similar triangles. So there are three prerequisites that you should know to understand Einstein's proof. Number one is, let me get the name of the proof. Okay, so it is book 1, proposition 32, that shares that three angles of a triangle, their sums will be 180 degrees, which is a constant. So that means if I have another triangle, the sum of these will also be 180 degrees. So this is Euclid's book 1, proposition 32. The second one, let me again make sure I'm not making a mistake, is it deals with area of a triangle. So if it is a triangle ABC and I draw perpendicular AD, so the area of this triangle ABC will be half of the base and perpendicular. And this is book 1, proposition 41 of Euclid. The same great Euclid, whose proposition 32 told us that it is 3 angles will be 180 degrees. And the proposition 41 of the same book tells us that area of a triangle is half base and the perpendicular from the opposite vertex. So if it were a right angle triangle, this will be the area of the triangle ABC will be half of AB BC. So this is the adjacents. So we will use this proposition of Euclid in the Einstein's proof. Einstein used that. And the third one is not very commonly known. This is book 6, proposition 4 by Euclid. And this deals with relationship between similar triangles. So let me draw two similar triangles, and the easiest way to draw a similar triangle is just I copy and paste the same triangle. Okay, and I will name the triangle differently. Okay, and so let's name it PQR, and the similar is what has happened to my okay. Okay, so let me remove those lines. Okay, so we have two triangles ABC and PQR, and I'm using different colors. So and let me also number them to avoid any confusion. Okay. So we have triangle ABC and we have triangle PQR, and the relationship is this, that let me use the color black. So angle BAC is angle QPR, angle ABC is angle PQR, and angle ACB is angle PRQ. So 1, 1, 2, 2, and 3, 3. So this Euclid's book 6, proposition 4 tells us that the corresponding sides, the ratio, are the same. So this is, let's start with angle 2. The opposite side of angle 2 is AC here and PR here. So PR divided by AC will be equal to PQ, which is opposite angle 3, PQ divided by AB, and the side QR divided by BC. So this is the law of proportionality between similar triangles, and I recommend you that you should, for the sake of curiosity, you should go and read this proposition. So these three principles Einstein used to prove Pythagorean's theorem. Now, number one is that the three angles of a triangle are 180 degrees and they remain constant. Number two, area of a triangle is half of perpendicular multiplied by base, and for right angle it is half of multiplication of adjacent sides. And this is the big one, is that the ratio of corresponding sides of similar triangles are constant between two triangles, which is written here. So now we have these three. Now let's work on the proof. I am cleaning up the space. Okay. So here is our right angle triangle. It has got three sides, A, B, C, and we'll prove using Einstein's method that hypotenuse square is equal to the sum of the adjacents square. So AC square is equal to the sum of AB square and BC square. So the first step is that we draw a perpendicular from the vertex of the right angle to the hypotenuse. So now we have three triangles. So let me copy the triangles so that we can visualize the three triangles separately. So this is triangle number 1. So let me draw it here, and then let me erase. We need to have D. Okay. And now let me capture the third triangle. So as I had promised, I'll go very slow. Okay. So now let me again. Okay. Good enough. So we have triangle ABD ABD and triangle DBC. So this is the right angle. This is the right angle. And this is A and this is A. And at this time, let me erase the line so that we see things clearly. Okay. So now let's look at the triangle ABC and ABD. You see that angle 1 is angle 1, angle 2 is angle 2. So because these three, ABC plus angle BAC plus angle ACB is 180 degrees, and angle ADB plus angle BAD plus angle ABD. So ABC is 90 degrees, ADB is 90 degrees, BAC and BAD are same, so they cancel out. So that means ACB, sorry, here is same as, so angle ACB in this triangle is same as angle ABD. So we have, this is our triangle 1 and triangle 2. So 1 and 2 are identical. That we proved. I went very slowly, but you know the purpose. Now let's look at, let me clean this area. You can always rewind the video a little to see what I have done. Okay, so now let's compare area ABC and area DBC. So this is right angle, this is right angle. Let me write it 1. Now C is common to both. So this is green. And by the same law, Euclid's proposition that the three angles are 180 degrees, we can show that so we can show that angle BAC is equal to angle DBC. Okay, let me just do that. So angle ABC plus angle BAC plus angle ACB is 180 degrees. From the third triangle, angle BDC plus angle DCB plus angle DBC. Okay. So this is 90 degrees. So is this 90 degrees? Now ACB and DCB are same. So we can eliminate those. So what we are left with is that angle BAC from this triangle is same as angle DBC. So now we have proved that these triangles are identical. So now something that most treatments don't do is that I will manipulate the diagrams to align them. So let me move this below. Okay. So I want to orient this one to appear like this. So color black. Let me put D. Let me put D here and A here and B here. So I am flipping the triangles like a butterfly. So they are symmetric. And let me draw the angles so that I just flipped it. And now I will rotate it like this. So when I rotate it, okay, almost. So A, D, and B. So this we have shown this is A, this is the right angle, and this is the, and now I can safely put the numbers of the angles. So this is 1, this is 2, and this is 3. Now it's a little tricky to orient this one so that B goes to the top. So first I draw D here, the point. So basically I have rotated it like this. So that will put B here and C here, and then I will flip it. So when I flip it, my goal is to bring C here. So, and let me draw the angles so that we don't lose sight of them. Okay. So now, as I promised you, I'm going very slow. So I rotate it like this. So now the triangle I have here, D, and blue here. I want it color green here. Okay. So I will rotate and flip one more time, and I'll draw the third triangle here. So D remains here, B here, and C here. So this way I have the three triangles side by side with the similar angle located at the same position. I was having difficulty visualizing this without going through this process. So now we apply Euclid's proposition 4 of book 6. Okay. So we have three triangles. This is triangle 1, 2, and 3. So the area of triangle 1, which is ABC, is half AB and BC. The area of triangle 2 is half AD DB. And area of triangle 3 is half BD multiplied with DC. This is Euclid's, Euclid's book 1, proposition 41. And because triangle 2 and 3 came out of ABC, we know that area of ABC is equal to area of ADB plus BDC. Okay. Now apply the principle of similarity between 1 and 2. Okay. So AC in triangle 1 is opposite of 90 degrees, and AB is opposite of the right angle. So I can safely say AB divided by AC will be equal to, now let's look at opposite of angle 2. So BC DB, so DB divided by BC and the opposite of 3 is here, so that is AD, and opposite of angle 3 is AB. So we get this relationship by Euclid's book, book 6, proposition 4, proportionality of similar triangles. So now let's solve this. dB will be equal to AB multiplied with BC divided by AC. So I'm using this relationship. Okay. And AD will be, and now I'm doing these, AB multiplied with AB divided by, again, AC. So this is AB square divided by AC. So area of this triangle over here, half dB. So area of the triangle is half AD. I think I've gone a little below. Okay. AD multiplied with dB is half of AB multiplied with BC multiplied with AB multiplied with AB divided by AC multiplied with AC. So this is half AB BC and AB square. Okay. You'll be tempted to make it AB cube, but let's not do that, and you will see the reason pretty soon. So let's copy this over here so that I can reuse the real estate for the third triangle. All right. So now let's look at triangle 1 and 3. So it's the same pattern. In fact, let me move this even higher. Okay, and we'll come back to it. So the opposite side to right angle is AC, and here it is BC. So BC divided by AC is equal to BC is equal to, let's take the opposite of angle C here. So BD divided by AB and is equal to so I have already taken BC divided by AC, BD divided by AB, and CD divided by BC. And this is the area of this third triangle, half BDDC. So BD will be AB multiplied by BC divided by AC. It's the same thing we had gotten before, and it is this relationship. And now let's make use of this relationship. So CD is BC square divided by AC. This is the beauty of symmetry. Beauty of symmetry. So area of the third triangle was half BD multiplied by DC. So BD is here, half AB multiplied by BC divided by AC, and CD is BC square divided by AC. So simplifying this, half AB multiplied with BC multiplied with BC square divided by AC square. So this is the area of the third triangle. Now let me draw this line again, and let me move this above for safekeeping. Okay. Okay. So okay, let me put it here. So if you still remember that ADB is triangle 2, BDC is this triangle 3, and ABC is equal to triangle ADB and BDC. So now let's write down the formula of the three triangles. So triangle of ABC, the area is simple, half base adjacents. So AB and BC. Now the triangle 2 is that I had kept it here. Okay. And triangle 3 okay. So this is the area of the whole triangle, perpendicular, base, adjacent. This is the area of the first triangle, ADB, and this is the area of the second triangle, third triangle, which is C. So now this is half AB and BC, and from this side I can take the common factors out. So AB, BC, AC square are common. So they will cancel. So this is, we are left with 1 here. And this side is AB square plus BC square divided by AC square. So AC square is AB square plus BC square. So this is the Pythagorean theorem. AB square plus BC square is AC square, and this is the Einstein's proof. And I apologize for a very slow method, and the 3 propositions of Euclid in use. Euclid's book 1, proposition 32, book 1, proposition 41, book 6, proposition 4. I hope you enjoyed the video, and this is for my students at Science Academy, Dalan, Katihar. Yes, Katihar.org. The